In this video, we'll see about the Hermite's special function, and the Hermite's special function is a solution to the Hermite's differential equation. So the Hermite's function. So the differential equation here is nothing but d square y, so the second derivative. So this v is just a number. So this v is just a number. You can take it as it will be a number. So just like we had n in our Legendre function, we had the number n. So here this v can be any number in this Hermite's differential equation. So so v is just a parameter. So v is a parameter. Now we'll assume a solution to this differential equation in the form of a power series of the given form. Okay, so this is the power series solution to this differential equation. You have to determine its coefficients. So now we have to find dy by dx. So dy by dx of this function. Now derivative, general formula I use for derivative of x of n is nothing but n xn minus 1. So that is the formula we use. So constants you'll have to keep them as you'll have to take them out. We won't differentiate the constant, just take it out, keep them as common, and just differentiate the x quantity. And the second derivative likewise. So now we substitute these values, y in this place, first derivative of y in this place, and second derivative of y in this place, and this differential equation now reduces to this form. This gets simplified when you substitute all this. You can simplify it to this form. So we get so this is what it simplifies to when you substitute these values, these the first y versus derivative of y and second derivative of y in this differential equation, and it simply the differential equation simplifies to this form. Now, what we have to do now is we have to find the values of the coefficients. Okay, what we'll do is we'll equate the, just like we did in the previous cases, we'll equate the coefficient of x power k minus, we put r is equal to 0, we will put r is equal to 0 and equate the coefficient of x power k minus 2, k minus 2. to 0, or to the terms on the right hand side. Terms on the right hand side are all 0, therefore we equate to 0. So, so what we do is here now, when we put r is equal to 0, we get this term becomes x bar k to the power minus 2. So the coefficient of this term is this, and the ar gets added on from the multiplication with the, when you multiply this term, when you remove the brackets and multiply, the ar gets added on. Therefore we have, this is what we have. So we have, when you substitute r is equal to 0, this is what we have: a naught k minus 1 is equal to 0. Now, obviously, the first term in the power series cannot be 0. So a naught is not 0, therefore these two terms have to be 0. So therefore we have two values of k from these two terms being 0. K can either be 0 or k can either be plus 1. Then this equation will hold good. So, so we have two values of k, which is nothing but 0 and 1. So a naught is equal to, not equal to 0. Therefore, we have k is equal to 0 or 1. 0. Okay. So now what we do is, now we do the next part. We equate the, we put r is equal, we equate the, to 0 the coefficient of the second term k x to the power k minus 1. So I put r is equal to 1. Okay, so when I put r is equal to 1, what will happen here? R is equal to 1, and equate the coefficient of x bar k minus 1. So therefore, when I put r is equal to 1, this term will become x to the power k minus 1. So therefore, this coefficient is what you have to equate to 0. And here you have a, this ar will become a1 and will get multiplied to this quantity. So you have a1 k k plus 1. So now when we substitute the known values of k, 0 and 1, we will know that this term k and k plus 1 is not 0. Therefore, a1 has to go to 0 for this equation to be valid. So therefore, a1 is 0. Therefore, a1 is 0. Now, in the next step, what we're going to do is, we are going to equate the coefficient of x bar k plus r to 0. So therefore, I am equating the general term, the coefficient of the general term x bar k plus r to 0. Now, if we are equating this as here, if the term is x bar k plus r, this term, for this term also to be x bar k plus r, here in the place of r, I have to substitute r plus 2, okay, because there is a minus 2 here. So the replace here in this term and in these coefficients, everything replaced by r plus 2. Therefore, this term also will become x bar k plus r. So and then just equate to 0. So therefore now we have, so when I equate this first term to, when I'm equating this first term, I get an AR from this number that is there, from this coefficient that is there outside, that gets multiplied here, AR, and I get a minus sign here, I get a minus 2 here, so minus 2 AR, so minus 2 AR, minus 2 AR, and then the terms in the brackets, k plus r minus b. And now this term. Now when you come to this term, you have to remember to replace r by r plus 2. Wherever r is there, replace by r plus 2. Therefore, we have plus ar plus 2. So this term that is outside this ar gets multiplied here into the brackets, and then we have the terms in the brackets. So wherever r is there, replace by r plus 2. So this is what we have. Now from this we can get a relationship between AR plus 2 and AR. So from this we get a relationship between. So this is what will help us find the values of the coefficients. So AR plus 2 This is what we get. Now I will substitute the two values of k. So we need two cases. We'll need the case for k is equal to 0 and k is equal to 1. So for both cases, I will just substitute this term and keep it. For k is equal to 0, I will substitute here. K is equal to. So for k is equal to 0, this equation just becomes now. This is for k is equal to 0, this is for k is equal to 1. Okay. So now next step is to write the solution itself. Now we have to find the coefficients and write the solution. So that is what we'll do the next step. So for the case k is equal to 0, so for the case k is equal to 0, when we substitute r is equal to, so r is going from 0 to 1 to 3 and so on, and the goes up to infinity. So when you go substitute like that, we get, so a1 is 0, because of which a3, a5, a6, a7, all of these terms up to a2r plus 1 terms will all be 0. So all the odd terms are becoming 0 here. Okay, so all the odd terms are becoming 0 here. And then we have, for the even terms, now a2 nothing but minus 2 divided by 2 factorial v a naught a naught. And we have a4 is nothing but minus 2 square v minus 2 a naught divided by 4 factorial. So a2r is nothing but a2r. So the general formula is a2r is equal to minus 2 to the power of r v minus 2 v minus 2r plus 2 divided by 2r factorial multiplied by a naught. I think I made a small mistake here, so just let me go back and correct it. When k is equal to 0, a1 can either be 0 or not be equal to 0. So there are two cases available here actually. So let me just go back to where we. So here a1, when a1 is equal to 0, so when k is equal to minus 1, a1 is equal to 0. So a1 is equal to 0 when k is equal to minus 1. That is the case, the first case. And then we have when k is equal to 0, when k is equal to 0, a1 can be 0 or cannot be 0, or may not be 0. a1 may or may not be 0. So there are two cases here that we have solved. We've solved only the first case so far. So we've solved the case where k is equal to 0 and a1 may be 0. So where we've taken the case where k is equal to 0, where we've taken this case where k is equal to 0. When k is equal to 0, a1 may be 0 or may not be 0. So we solve the case where a1 is 0. We have to also solve the case where a1 is not 0. So in that case, we have our relations. So a3 will be minus 2b minus 1 3 factorial a1, and a4 would be, a5 would be minus where b minus 1 b minus 3 a1 5 factorial. So all this comes from this relationship. So when you put a1 here, you would get ar plus 2, which is nothing but, so you get ar plus 2, which is nothing but a3. So when you put a1 here, you get a3. So likewise you keep getting. This is so the general formula here for the case of odd coefficients will be a2r plus 1 is equal to minus 2 the power of r, b minus 1, b minus 3, and it's a sequence going up to, sequence of terms going up to b minus 2r plus 1 multiplied by a1. The denominator is nothing but 2r plus 1 factorial. So from this we have coefficients for even, so coefficients for the even terms and coefficients for the odd terms, all in terms of a naught and a1. Okay, so all in terms of a naught and a1. So now I'll just write out the solution for this now. So the combine everything together, put them in the power series that we defined here. Put them in the power series. All terms a naught, a1, a3. So this power series contains all terms, so up to infinity. So we have the coefficients for both terms, and we combine both the cases, and we write the solution for in a general way. We combine both the cases and we write solutions for in a general way, including even coefficient terms and odd coefficient terms. So even coefficient terms are in terms of a naught, odd coefficient terms are in terms of a1. So we'll just write them out now. So I'll write the solution in the new page. Now solution contains all terms. So it's of this top. A naught, one minus so it's the first term a naught, and then you have the second term which is comes from a2. So this was the term we wrote out for a2. So and then we have a sequence of terms going up to the general term. The general term sequence of terms going up to the general term is nothing but minus 1 the power. So this is the general term that we wrote out here for a bar, that for the even terms in terms of a naught. So this is the general term that we wrote out, and we have the power of x coming from x to the power 2r coming from the power series. So we assume the power series of this form. So it comes from the power. The x term comes from the power series. And then we have the odd terms. So odd terms are in terms of a1. So a1 is common, and then we have all the odd terms. So the first term is a1, so that is 1 minus 2 minus 1 factorial x. So it's a sequence of terms going up to the general term, which is nothing but so these will have odd powers of x, so therefore I will take another x out, so that therefore this will have all odd powers of x. So the first term will be x, second term will be x cubed, the next term will be x to the power 5, and it goes on like that. So the x I pull out to make all these terms inside are odd powers of x, because we are talking about odd coefficients and odd powers of x here. So this will be your general solution for k is equal to 0 case. Now for next case, k is equal to 1. So for k is equal to 1, so case 2, k is equal to 1. So this is a much simpler case because when k1 is 0, k1, k is equal to 1, we had already said that a1 should be 0. Then a1 k is equal to 1, then a1 is 0 already. Then a1 is 0, so therefore we have only even number of terms. Okay, so therefore we have only even number of terms. So, so we put r is equal to 0, 1, infinity. That many terms, and we have the general relationship. I'll directly write out the general relationship between the, so the second term coefficient is nothing but -2, b minus 1, 3 factorial, and the fourth term in terms of a naught is nothing but -2 r square, b minus 1, b minus 3, a naught, 5 factorial. So similarly we can write out the other terms. So we can directly write out the general term. So I'll write out the general term here. A to r equal to -1 to the power of r 2 square b minus 1, b minus 3, sequence of terms going up to b minus 2r plus 1 multiplied by a naught. And the denominator 2r plus 1 factorial. Therefore, the solution now in this case would be y would be equal to a naught x. So a naught would be the first term. So I'm writing an x here because a naught x here because the first term itself in this series will have a naught itself will have a power of x. Okay, because we had assumed our series to be of the form x to the power k plus r. So even if r is 0, k value is 1. So when r is 0, a value is a naught. But x, there is already x term because k value is 1. So therefore we have to write the x factor here. So therefore we write the x factor here. So a naught x 1 minus 2 b minus 1 and goes up to the general term, which is nothing but -1 to the power r. Okay, so these are the two solutions to the Hermite polynomials, and taken in linear combinations, they'll give you the two solutions. So for both the cases. So now we'll to the Hermite differential equation. These are the two solutions. Now we see what the Hermite function is. So the Hermite function is the solution in this written this way. So this y can be written, the y that we wrote out as a solution to the differential equation can be written out this way. little order as a to the n summation summed over m going to n by 2 x to the power n minus 2m. And divided by m factorial divided 2 to the power 2m m factorial n minus 2m factorial n minus 2m factorial. Now what is n? N is nothing but the number of terms you want in the series. So n is nothing but the number of terms you want in the series. So why we do this is because how we get here is because we want the solution in descending powers of x. Okay, so we want the solution in descending powers of x. So therefore, it is particularly advantageous to do that for some reasons. Therefore, what we do is we go to this equation that we wrote out here, this equation, and turn it into a equation that gives us descending powers of coefficients. So supposing you have, let's say, we'll rewrite it in this following form. We'll rewrite this equation in the following form. We'll also replace this b by n. So we'll also replace this b by n. Okay, so we'll also replace this. Also replace this b by n, and we will write the equation in this following form. So I'll write it in. So before we had it as r plus 2 was this side. Now we're bringing r here this side because we are writing it in descending powers. So from higher we are going to lower powers, the power series. So we want the descending powers, and now b I am replaced by n. R plus 2. Now I said I wanted descending power, so wherever I have r, I will actually replace by r minus 2. Okay, so to get that descending power thing going. So wherever I had r, I will replace by r minus 2. So this term will now just become ar minus 2 is equal to minus, here r, if I replace by r minus 2, I'll get r minus 1. Here if I replace by r minus 2, I'll get just r. I'll have only r. And denominator, if I replace r by r minus 2, I will have n minus r minus 2. So if I take the minus inside, I will just become n plus r. So there was already a minus sign outside, so when I multiplied it with the minus that came from r minus 2, it just became plus. So this was what we have. So now, and we have here, of course, where r, if I replace by r minus 2, this term will become ar. So now from here we can get the in descending terms. So supposing if I'm going from higher to lower powers, okay, so I pick a higher power, but now we are going in even coefficients. So r n minus 2, n minus 4, n minus 6. So from higher to lower we are going. Therefore, I will have coefficients like this. So again, I can substitute for this an minus 1 in terms of an and get everything in terms of an. So I have a series solution of our differential equation in descending powers of x from higher to lower. So from that's where we get this equation now. From that's where we get this equation. Now this equation is nothing but this kind of a expression. So it is a power series that is going from higher to lower in even number of terms. So it's going like that. So this is the equation. So this equation where an has a particular value. So this n is nothing but now this n. So this an where this an has a particular value, wherever this an has a particular value of where an is equal to 2 to the power of n. Okay, so where an is equal to 2 to the power of n. This solution is called the Hermite function. Okay, so this solution is called the Hermite function. So where an is equal to 2 power n. So if we box this out, this is your Hermite function. So that's it for this video. So hope that was helpful. I think it turned out longer than I thought. So we've studied about the Hermite differential equation, solved it, and also obtained the Hermite function in this case.